Have you ever chased a phantom safety fault for hours? Or just had that nagging feeling, wondering if your safety system is really as safe as it should be? Well, today, we're going to demystify a key player inside Rockwell's GuardLogix controllers, the CROUT instruction. Honestly, if you get this right, your machines are not only safer, they're a heck of a lot easier to troubleshoot. But get it wrong, and you are in for a world of headaches. Let's dive in.
So first things first, let's set the stage. Just imagine this. You slam an e-stop button, but the machine, it just keeps going. The safety contactor, the big physical switch that's supposed to kill the power, got the command to open, but it didn't. That silent failure is exactly what we're here to prevent.
And that exact scenario leads us straight to the core danger here, what we call the welded contact problem. This thing is a silent killer for safety systems. It's a failure you literally can't see, but it's one that can have catastrophic consequences, completely bypassing all the protections you thought you had in place.
So what exactly is a welded contact? Well, think of it like this. The internal metal points inside a relay or a contactor get so hot from use that they literally fuse together. So the controller sends the off signal, but that physical switch is stuck in the on position. Your system thinks it's safe, but the machine is still powered up and dangerous, and that's the critical disconnect we have to solve.
Okay, so this is where our hero comes in, the CROUT, which stands for Configurable Redundant Output Instruction, is specifically designed to catch this exact failure and a whole lot of others too.
So how does it work? It's a really smart three-step check. First, it always uses two outputs, for redundancy. Second, and this is the really critical part, it watches a feedback signal that comes back from the device, which confirms its actual physical state. And finally, it acts like a watchdog. If that feedback doesn't match the command within a specific amount of time, bam, it trips a fault. It never ever just assumes its command was obeyed.
Now, to really appreciate why the CRUT-R is such a huge step up, it helps to look at what it replaced, the older, more basic ROUT instruction. Let's put them side by side.
Looking at this table, the big difference just jumps right out at you: flexibility. With the old route, you were locked in. You had one feedback type, one fixed reaction time, and that was it. The CROUT, on the other hand, adapts to your design. You get to tell it if you're using normally open or normally closed contacts, which can make wiring way simpler. You can fine-tune the reaction time to stop nuisance trips on slower devices, and most importantly, when something does go wrong, it gives you these detailed error codes, not just some generic fault, which can slash your troubleshooting time.
So really, it all boils down to this. The CROT is the clear winner because it's just plain smarter. It adapts to your hardware, it gives you specific, actionable data when things go wrong, and it even does a health check on its own hardware. That's why, for any new design, it's a no-brainer. But, knowing why it's better is only half the battle. Now, let's talk about how to actually use it correctly.
All right, theory is great, but let's get practical. The CROs is incredibly powerful, but boy is it sensitive to how you wire it up. Let's break down the most common mistakes that will have you pulling your hair out on the factory floor.
Okay, listen up, because this is the big one. By far, the number one mistake is a mismatch between what you configured in the software and what you actually did in the panel. Are you using positive or negative feedback logic? If you get this wrong, you will get an immediate fault, guaranteed.
This table right here shows you exactly why that mismatch is such a problem. Let's break it down. Positive logic usually means you're using a normally open contact. So when the device turns on, that contact closes, and the CROUT expects to see a 1. Makes sense. Negative logic, on the other hand, uses a normally closed contact. So when the device turns on, the contact opens, and the CROUT expects to see a 0. If the physical reality in your panel doesn't match the setting in your software, you get an instant fault. It's really that simple, but it's so easy to get wrong.
Okay, so besides that logic mismatch, here are 3 other common traps. First up, voltage drops. If your 24-volt supply sags, even just a little, your relays might not energize fast enough, and that can lead to a timeout fault. Second, series wiring. Look, to save on inputs, sometimes you wire 2 feedback contacts in series to one input terminal. That's totally fine, but you must assign that one input tag to both feedback parameters in the software. If you don't, the CRO is only listening to one of them. And finally, the reset. It needs to see a rising edge, a change from off to on. You can't just tie it high and expect it to work.
Now, we get to the best part about the CROUT. It's diagnostics. See, when a fault happens, it doesn't just fail. It tells you why it failed with a specific hex code.
It's like a built-in troubleshooter. So let's decode the ones you're going to see most often.
All right, first up, you're looking at your logic and this code pops up. Hexadecimal 5003. What in the world does that mean?
This code means the instructions saw a feedback signal turn on when it was absolutely positively supposed to be off. And the classic cause is that logic mismatch we just talked about. You told the software, hey, I'm using a normally open contact, but in the panel, you wired up a normally closed one. The moment the machine is idle, that NC contact is sending a 1, and the CRO freaks out thinking the relay is already welded shut.
Okay, next on our list is fault code 16 hex 5006. This one is all about timing.
Yep, this is your classic timeout fault. The CROUT sent a command to turn its outputs on or off, and then it started a stopwatch. It waited and waited for the feedback to change, but the signal just never showed up in time. This could be a slow-acting relay, a loose wire, or that sneaky low-voltage problem we just mentioned.
And finally, one of the most frustrating ones to diagnose, fault code 16 hex 5000.
Now, while this code can point to a few things, a major culprit is a hardware problem, and specifically low panel voltage. If your 24-volt supply is sagging down around 22 or 23 volts, the safety relays might not have enough juice to pull in cleanly and reliably. This can cause a persistent 5000 fault that just won't clear until you cycle power. It's a fantastic place to start your troubleshooting.
And this really gets to the heart of why the CROUT is so valuable. Just like the quote says, it gives you more information about what it's doing without making things way more complicated. It's not just about ticking a box for a safety standard. It's about building systems that are smarter, more resilient, and honestly, way easier to diagnose when things go wrong. And that really leaves us with a final question to think about for your own work. Is your safety system just functional? Does it just meet the bare minimum requirements? Or is it truly intelligent? Is it actively monitoring itself and giving you the feedback you need to prevent failures before they can even happen? Thanks for tuning in.